Let's review some properties of exponents. We recall that x cubed means x times x times x. The exponent-base relationship is this, that when we see an expression like this, x is the base, 3 is the exponent tells how many times the base is used as a factor. So here we have 3 factors of x. We can write this as x times x times x. When 0 is an exponent and the base is not 0, then the result is simply 1. So any base to the 0 exponent is equal to 1 except 0. X to the negative 2. Now a negative exponent implies a misplaced base. We can think of it like that. This is 1 over x squared. So 1 over x squared. Negative exponent says misplaced base. Now, this holds true if that base were in a denominator. It would be misplaced. You see, we put this into a denominator to make it, or to put it into the right spot. But what if we had 1 over x to the negative 3 to start with? You see, then we would say, oh, the base is misplaced. Let's send it up into the numerator, and it becomes x cubed. And then nothing is left in the denominator. So it's over 1, and I'm writing it for emphasis. We would just write this as x cubed in most cases. The cube root of x equals 5. If we have this, if we have cube root of x is equal to 5, then we can say that x is 5 cubed. That is, to go from this form to this form, you can think of it like this. It's strictly an algebraic situation. To undo the idea of cube rooting, you cube. You see, so it's that cubing and cube rooting are inverse operations. So cube here to get x, cube over here, and we have 5 cubed. So these are equivalent forms. Now, this would work equally as well if the index of the radical were 5 or 7 or 10 or 2 or whatever. You do the inverse operation by raising to this as an exponent, you see. On both sides, and so we'll have the index of the radical appearing as an exponent on the number to the right. Now, this is an interesting situation. One of the most commonly made mistakes is to confuse these two forms. Negative 4 squared. Now notice negative 4 is in parenthesis, and it means that negative 4 is the base of that exponent. So we have 2 factors of negative 4. It means negative 4 times negative 4 is 16. However, if the parentheses are not in there, then the base of the exponent 2 is 4 and not negative 4. You see, this is the negative of 4 squared. That's the way to think about it. So it's the negative of 2 factors of 4, and the result is negative 16. Here's another situation, 5 to the 1/2 power. 5 to the 1/2 power is the square root of 5. Fractional exponents imply radicals. The denominator of a fractional exponent implies the index of the radical. And the numerator is just a common, ordinary, everyday household exponent, you see. So 5 to the 1/2 square root of 5. Now let's take an example of this form. Fractional exponents. All right, 8 to the 2/3 power. It means that we have an exponent 2 on 8. We also have the cube root of 8. You see, so we're performing these 2 separate operations on this base of 8. We can think of it like that. Now, it doesn't make any difference which of the 2 operations you perform on 8 first. That is, we could think of this as the cube root of 8 squared like this. Now, I've written the same problem over here, and I'm working it another way. I'm thinking of this as, well, let's apply cube root on 8 first and then square. You see, we'll get the same result. And here, 8 squared is 64. The cube root of 64 is 4. Here, the cube root of 8 is 2. 2 squared is 4. We get the same result as expected. So just think of this as being 2 operations applied to that base of 8, and you can apply either of them first. It's a little easier in most cases to apply the radical first because you deal with somewhat smaller numbers. If you take this base and raise it to the exponent, the situation can get a little bit out of hand if the numbers are large. In this problem, we're asked to evaluate when x takes on a particular value. Now, problems involving evaluation are handled by just replacing some letter with a number. Evaluate means to find the value of. So we want to find the value of y when x takes on this particular value. Now, there's a certain procedure involved in this process, and the procedure is to replace the letter with the number in the first step. And don't try to do any calculating in that first step. For example, here we write y equals, bring down the minus 8 and replace x with negative 4. Now notice I'm introducing a parenthesis so that this doesn't imply that we have two separate terms. We only have one term, negative 8x to the negative 2. And to maintain that idea, I need to introduce the parenthesis. But then we apply the exponent here. Now, this minus sign in the exponent is not related to these two minus signs. They're not even distant cousins. They mean entirely different things. These say the negative of 8, the negative of 4. And this is implying a misplaced base. Now, we need to take care of one thing at a time here. Now, this exponent is on this negative 4 as its base and has nothing to do with the negative 8. You see, we wouldn't want to multiply these two first and then apply the exponent, because then the exponent would be applying to the negative 8 as well. So what we'll do is this. We have a misplaced base here. Let's put that base in the right spot. It belongs in the denominator. Now this negative 8 stays in the numerator. The base of negative 4 goes into the denominator, and this exponent becomes positive. All right, now we'll apply the exponent to the negative 4. Let's see, negative 4 squared means negative 4 times negative 4, oh, that's 16. And then negative divided by positive is negative. 8 over 16 is 1/2. In this next one, suppose we want to evaluate this when x is equal to 3. Well, let's see, let's replace x with 3 and kind of follow our nose through it. So we have 2 over 3 to the negative 2 power. Now once again, we have a misplaced base. We have 3 as the base of the exponent negative 2. The negative says that this base is in the wrong spot. It needs to go up into the numerator. So this really should be 2 times 3 squared. Now we'll square the 3 to get 9. This is 2 times 9, or 18 for y. Here are some more situations involving exponents, and I'm sure this is a review. If we have x squared times x cubed, then we can evaluate this, simplify it, by adding the exponents. When we multiply like bases, we add the exponents. So this becomes x to the 5th power. Now the basis of this is just this, that this says we have 2 factors of x. This says we have 3 factors of x. All together we have 5 factors of x. So that's why we end up adding. Here we have x to the 7th divided by x to the 5th. The shortcut to this is to subtract exponents. We take, now notice, the basis of this though is that we have like, the basis of it is that we have like bases. But the x's are alike, and that's what allows us to deal with it in this shortcut way. All right, but the notion is that we're subtracting the exponents. We take the exponent that's in the numerator and we subtract the exponent in the denominator. 7 minus 5 is 2. Now the basis of this, the reason we can do this, is because we have a string of 7 factors here. We have a string of 5 factors here. These 5 factors will cancel with 5 of the 7 factors in the numerator, leaving us with 2 factors of x in the numerator. That's why we get x squared. If we have a term here involving a couple of factors raised to an exponent, we can think of that exponent applying to the factors separately. We can think of it like that. That is, we can think of this as 4 cubed times x cubed. Now, another way to think about it, and it's okay, is to say we have 3 factors of 4x. We could say 4x times 4x times 4x. Now, that'll all come out in the wash. You can work it either way, but this is just one way to think about it. 4 cubed is 64, and then bring over the x cubed. If you had 4x times 4x times 4x, that also would be 64x cubed. An exponent applied to a fraction means that the exponent can apply to the numerator and denominator separately. Here we could write this as 5 squared over x squared. 5 squared, 25 over x squared. Raising a power to a power. Now recall that when this occurs, you multiply the exponents. That's the shortcut. So it's x to the 2 times 3, or x to the 6th power. If you get confused about that, though, and don't remember the shortcut, then just go to the basis of what exponent means. Here we have 3 factors of this as the base. You see, so this really means we have 3 x squares. We have x squared times x squared times x squared. Oh yeah, we add the exponents, it's 2 and 2 and 2. Oh, that's 6, x to the 6th power. So if you get into a jam, just go back to the basis of what exponent means. Let's take a look at a few examples that illustrate the use of exponents. Here we're multiplying a couple of single terms, and in that circumstance we generally think of it like multiplying numbers times numbers and like letters times like letters, and just apply the rules of exponents when we involve the letters. But here 4 times 3 would be 12, and then x squared times x to the 5th is x to an exponent, which is 2 plus 5, 7. When radicals are involved, a lot of times we can just change the radical form into a fractional exponent form and use the rules for exponents. But here we have something else to do as well. We're squaring 3x. It means we have 2 factors of this term, 3x. So it's really 3x times 3x. We could think of it as applying the exponent 2 to both the 3 and the x. So for this part of the problem, we get 9x squared. And now let's go through that process I mentioned before of changing the radical into a fractional exponent. The index of the radical indicates the denominator of a fractional exponent. So this is really x to the 1/3 power. Now the 1 can be thought of as the sort of the naturally occurring exponent on x. This is x to an understood 1 power, you see. So x to the 1/3 for the overall factor. All right, now when we multiply, we're multiplying the like letters, we add the exponents. So we'll bring down the 9, x squared times x to the 1/3. 2 plus 1/3 is 2 1/3. Or we could say it's 3 times 2, 6 and 1, 7, 7/3 if we want to. So it's x to the 7/3, I think is probably the way it would be listed in the back of the book in an answer set. You know, that's another topic I wanted to mention here, that a lot of times you might write your answer in one acceptable form, and then you'll find another acceptable form when the solution to the problem is listed in the back of the book or in the solutions guide. So, and it's important to realize that when you have a correct solution to a problem. Well, let's take another one. Here we have fractions involved, and we have an exponent. We're raising a power to a power here. We have an exponent on an exponent, so we need to resolve that situation certainly early on in the problem. So I'll bring down the numerator, and in the denominator, remember that in this circumstance we just multiply the exponents. So this is x to the 1/2 times 3. Think of this as 3 over 1, and multiply numerators times numerators, denominators times denominators for these two little fractions. So it would be 3 over 2. And now, to resolve this situation, when dividing like letters, we subtract the exponents. So this is really 3x to an exponent, which is 2 minus 3 over 2. And I'm emphasizing what we're thinking by writing this step. You wouldn't always have to write this step, but this is what the calculation amounts to. So this is 3x to the, well, let's see. This is 2 minus, now 3/2 is 1 1/2. So this is nothing more than 2 minus 1 1/2. Oh, that's 1/2. So 2x to the 1/2 power. Now the answer could be written this way, or the answer could be written as 3 times the square root of x, because the fractional exponent, remember the denominator implies the index of a radical, so this is square root then of x. Here's another one. Notice in the denominator once again we have power to power, so this is 5x to the 4th. And then in the denominator, x squared cubed is x to the 2 times 3, or x to the 6th power. Now, we can take a couple of approaches at this point. If you take the approach that we used on the previous problem, then you would subtract the exponents. You might think, well, this is 5 times x to an exponent, which is 4 minus 6. 4 minus 6, and I'll emphasize it here like this, is -2. So this is 5x to the -2, but generally we don't write a negative exponent like this. We put the base of that exponent in the appropriate place, numerator or denominator. So we would write this as 5 over x squared. Now another way to think about it, another way to approach the problem, now remember the answer is 5 over x squared. Let's go back up here. We could resolve the situation right here. We could say that these 4 factors of x will take out 4 of the 6 factors of x here. You see, leaving 2 factors of x in the denominator. So we could very quickly arrive at an answer like this. We could say, all right, all of these factors of x will cancel with 4 of these, leaving x squared down in the denominator. So it's 5 then over x squared. And that then is our answer. Here we have a negative exponent to begin with. And once again, there are a couple of ways, a couple of strategies to go about simplifying the expression. Now, if we just go straight at it, that is, multiply as we saw in the earlier problems, where it's numbers times numbers and like letters times like letters, that's the fastest way to deal with it. Understood 1 as the coefficient here times 2 is 2. And then x to the negative 1 times x squared is x to an exponent, which is the sum of these. Just bring them together. Negative 1 with 2, oh, that's 1. So this is simply 2x. Now, another way to see it is like this. Actually, I'll just rewrite it right here. You see, the negative exponent says this base is misplaced. So we could leave this factor in the numerator, and then this moves down to the denominator, and then we see, oh, this x cancels with one of those 2 x's, leaving 2x as our answer, as expected. Here's another one. Now, notice we have here, we have a radical and we also have a negative exponent. And we have to deal with both of those situations. I would probably do this. In the numerator, I would think of this as negative x to the 1/2 power. And now, at the same time, I'm going to kick this x to the negative 1 up into the numerator and just write another factor, and it is simply x to the 1 power, like that. And the 5 stays in the denominator. Now, there is another way to think about this. I mean, the 5, you can think of all of the factors that involve letters as kind of a separate event from the notion of the number 5. And we could actually separate out, we could think of 1/5 times all of this business, you see, and that would be okay too. But I kind of favor staying within one fraction like this. It's a little easier for me. At any rate, we have, let's see, a minus sign is the sign of the fraction, and if you recall, a single sign, a single minus sign in a fraction can float into any one of 3 positions, the sign of the numerator, the sign of the fraction, or the sign of the denominator. And generally with answers, we want to show an answer as the negative of the overall fraction. So we would probably write it like this. Here's the fraction bar, x to the 1/2 times x. We're adding exponents. 1 plus 1/2 is 1/2 or 3/2. So we have x to the 3/2 in the numerator. In the denominator we have 5. Another acceptable way to write this would be like this. Now, I want to pay careful attention to this, because this is another one of those situations where another way to write this, another acceptable way to write this, looks quite a bit different from this. And it is like this. We're separating the idea of this understood 1 over the 5, and we can actually separate that numerical part like this, you see, and then you see how different these two look, and yet they mean exactly the same thing. Let's take a look at a few problems involving factoring. Now, we've seen quite a bit of factoring in the past, and we used factoring for particular purposes in the past. One of those purposes was to solve quadratic equations, for example. Now, in calculus, factoring takes on a whole new dimension, because it's often the case that we have to force a factorization or use factoring in order to create a particular form in an expression in order to apply a certain strategy in calculus. Now, so let's just review a couple of things, and we're going to take what we already know about factoring, and then we're going to look at a couple of nuances as well. Suppose we want to factor this completely. Now, remember, the first idea in factoring is to look for a common factor, and we look for the numbers that would be common in a couple of terms, and we look for the letters. Now here, x squared is common to both terms, so we just snag out x squared from both of these. Now, when we pull x squared out of this term, we're left with 2. When we pull x squared out of this term, we're left with minus x. And that's all there is to it. Now here's a nuance on this kind of theme. Suppose we're factoring here. Now the common factor, these look very similar to one another, but the common factor is still x squared. When we pull x squared out, here's what happens. We pull x squared out of this term and we're left with the 2 and 1 factor of x. When we pull x squared out of this term, all of everything that's there sort of comes out. And you know, there sometimes is some confusion about what do we need to put here? Well, just remember that with factoring, you should be able to multiply your factored form and get what you started with. So a lot of times you can tell what to write just by asking yourself, what do we need to put here in order to have x squared times that something in order to get this? And the something that we have is a 1. So when we pull all of a term out, when we're taking out a common factor, 1 is left in its place. All right. The next few problems involve fractional exponents, and we deal with those situations in much the same way that we deal with the situation before. Now here, let's take out the smallest of these two exponents when we come to the letters, but in terms of the numbers between 2 and 4, the common factor is 2. Now let's take out x to an exponent, which is the smallest of these two. Oh, it's the 1/2. So let's take out x to the 1/2. Now, what's left? Well, let's see. We're taking 2x to the 1/2 out of this term. Oh, we're taking everything out, so 1 is left. Now, we're taking the 2 factor out of 4 leaves 2. X to the 1/2. We're pulling x to the 1/2 out of x to the 5/2. Now remember, this is one of those cases where we might want to think about what exponent on x do we need to have in order for us to multiply these two and get x to the 5/2. Now, when you're multiplying like letters, remember you add exponents, so it is 1/2 plus what exponent that gives 5/2? Well, that's pretty easy to tell. Remember that 5/2 is just 2.5. So 1/2 plus what is 2.5? Well, 2. So that's how we might go through the thought process for this kind of problem. Now, for this one, let's see. Look at the numbers. No common factor. Now, look at the exponents on x. Well, let's decide to take out this negative exponent. You see, let's decide to take out x to the negative 1/2 power. Let's do that. X to the negative 1/2. Pulling x to the negative 1/2 out of this term leaves the 2. Now, here's the trick. Pulling x to the negative 1/2 out of this. Now, once again, remember, it's going to be x to some exponent so that we can multiply this and get that. And remember, when you're multiplying like letters, you add those exponents. So it's negative 1/2 plus what will give 5/2? Well, think of 5/2 as 2.5. So let's see. What with negative 1/2 gives 2.5? You see, now, if you want to, you can even come out to the side and think of it like this. I want some exponent that I'll call n, and I'm going to take 1/2 away from that, and I want that to be equal to 2.5. Now, what does that need to be? Well, you know, if we can't come up with it mentally, we can certainly come up with it over here. Add 1/2 on both sides, and we find that n to be 3. So that number that we need for the exponent is 3. So here is the factored form. Now, here's an enormous problem. Now, this one, it stretches from here all the way over to here. Now, let's just take a look at this. What we have here is two terms. We have a term here. Now, a term is an indicated product. So we have the product of 3 times this times this. And over here we have an indicated product, 10 times a couple of binomials raised to exponents. So those are the two terms. Now, we're going to pull out a common factor. So we're going to look first at the 3 and the 10. Oh, they have no factors in common. All right, fine. Now, we do see that we have x plus 1 here and x plus 1 here. So we're going to take out x plus 1 to some exponent. Let's decide to take out, well, here we have 1/2, and here we have 3.5, which is 1 and 1/2. So let's take out the smaller of those two. That would be 1/2. So we're going to snag out x plus 1 to the 1/2. And we're just deciding what to take out at this point. We're not factoring just yet. All right, here we have 2x minus 3 as the base. 2x minus 3 is the base over here. We have 5/2, which is 2.5. Up here, we have 3/2, which is 1.5 over here. Let's take out the 3/2. All right, so we have 2x minus 3 to the 3/2. All right, so we're just snagging this business out of all of this expression. Now I'm going to open a bracket, and let's decide what's left when we snag this out of this term. All right, when we pull these factors out, we're not taking anything from the 3, so the 3 is still remaining. When we pull x plus 1 to the 1/2 out of this, it's gone, so that's not there. Okay, now when we pull 2x minus 3 to the 3/2 out of this, we're left with 2x minus 3 to some exponent. So it's 2x minus 3 to some exponent. And once again, we have to think, gee, what exponent do we need here so that 3/2 plus whatever this is gives 5/2. Now, it might help to think of these as mixed numbers. So 1.5 plus what is 2.5? 1.5 plus what is 2.5? Gee, 1.5 plus 1 is 2.5. So the exponent here is 1. All right, now I don't need to write anything then. Okay, so I'm finished taking this business as a common factor out of there. Now let's pull this out of that. All right, so I'll put plus. Now notice that we're not taking any factors out of 10, so we have 10 times. Now, x plus 1 to the 1/2 is being pulled out of x plus 1 to the 3/2. Now remember, that's 1.5 and that's 1/2. We're pulling the half factor out. That's kind of a good way to look at it. And this is then x plus 1. All right, let's go on. We're pulling 2x minus 3 to the 3/2 out of 2x minus 3 to the 3/2. Oh, we're pulling all of that business out. So we're done here. Now it's just a matter of cleaning up. So we'll leave all of this alone. And the cleaning up is within the brackets. Whoops, excuse me. So we have, let's see, 3 times 2x minus 3, that's 6x minus 9. And this is 10x plus 10. And now we're just collecting over there. You might look at it for a second while I write this and decide what we're going to do. By the way, that notion of you doing a little bit of work while I'm doing stuff up here extends to the idea that if you want to take a shot at problems as they come up on video, I suggest that you do that. I suggest that you try a problem on your own. Stop the tape, write it down, stop the tape, try the problem on your own, roll the tape. You get a little extra practice in that way. All right, at any rate, here we have 6x plus 10x, that's 16x. And then minus 9 plus 10 is plus 1. And here then is our final factored form. Let's take a look at a few problems involving fractions. Now, there are 2 different strategies we can use to simplify fractions. One strategy is this. This is not the one we're going to use primarily, but I want to make sure we understand that it would be okay if we divided the 2x into each part of the numerator. It is a valid simplification, in other words, to say that this expression is the same as 3x squared over 2x plus x to the 4th over 2x. You see, and separate sort of into these 2 fractions and then simplify each of them, just reduce each of them as separate events. Now, the x's would cancel here, leaving us with 3x over 2. The x here cancels with one of the x's up here, leaving us with x cubed over 2. Oh, happy day, we have common denominators here, so we could write this as 3x plus x cubed over 2. And then we could factor in the numerator if we want to and write this as, well, let's see, let's take out an x from each of these 2 terms. We would have x times 3 plus x squared all over 2. Now, this is a valid way to approach things, but it might be a little more efficient if we do it like this. If we just factor in the numerator first and then look for cancellation opportunities with the denominator. Now, remember that a lot of times the way that we'll end up doing things in calculus is determined by the form that we want to achieve. And we'll know all about that when the time comes, so don't worry about it at this point. Don't be asking yourself, gee, I wonder which way we need to do this one. Well, it really doesn't make any difference right now, but I want to show you some of the techniques for dealing with situations involving factoring in the numerator. Here's what I mean. If we just look at the numerator and we take out the common factor, x squared, you see then we have x squared that we're yanking out of these two terms. Pull x squared out of this term, we're left with 3. Pull x squared out of this term, we're left with x squared. You see, and now just bring down the denominator, and we have a cancellation opportunity here. This x takes out one of those x's, so we have x times 3 plus x squared all over 2 as our answer. And this then is the same as what we have here, as expected. Here, another situation involving fractions. Here we have a couple of little nuances involving that radical and the fractional exponent. But let's approach it the same way that we did the previous one. That is, let's attack the numerator and factor in the numerator and then look for an opportunity to cancel with the denominator. So we're going to think of the square root of x as x to the 1/2 power. And now, in the numerator, we're going to take out, well, let's see. Now, we're going to take out a common factor. We'd like to take out a common factor of 1/2 and 3/2, which is the smaller of the two exponents. You see, that's generally the way we identify the greatest common factor. It's the factor whose like base, if we have like bases, we're looking for an exponent that is the smallest in those two. If we're looking at x squared and x to the 5th, then we take out x squared as a common factor. Remember, that's the way we do it. So we are identifying the smaller of these two. Oh, that's 1/2. So we're going to pull out x to the 1/2 from these two terms. When we snag x to the 1/2 out of this term, everything comes out, so we're left with an understood 1 here. And then pull the x to the 1/2 out of this, and we want x to an exponent such that 1/2 plus this is 3/2. 3/2 is 1.5. So 1/2 plus what is 1 1/2? Oh, 1/2 plus 1. Now I can emphasize it by putting a 1 here, but we generally wouldn't write that. We would just write this as 1 plus x. And now we have x in the denominator. Now we have a cancellation opportunity of some kind here. Now, remember that when you divide and you have like bases, you subtract exponents. And if you are talking about a situation and you want the x base to be left in the numerator, then we would write this as x to the 1/2 minus 1. You see this exponent minus that one times the 1 plus x. All right. However, this would leave us with a negative exponent, and we would have to kick it down to the denominator. Well, let's anticipate that and do this. Let's just say that we're going to cancel here. We're going to cancel a fast way by subtracting exponents, but let's take the exponent on x in the denominator and subtract the exponent in the numerator. So it's 1 plus x in the numerator, and then x to an exponent, which is 1 minus 1/2. 1 minus 1/2, oh, that's 1/2. So x to the 1/2. Now, it would be okay to write this as 1 plus x over the square root of x. These say the same thing. Now, in algebra, there was a technique for dealing with situations where you have radicals and denominators. A lot of times we were told, and we kind of told ourselves, that we didn't leave an expression like this. Well, sometimes we need to leave it like this because we are achieving another form elsewhere in the problem. So for right now, this is okay. We'll talk about rationalizing techniques in just a little bit in another section. Well, here's another problem. Now, the problem is all of this. And notice that again, we had a problem similar to this before. In fact, it was more complicated than this one. But we have a couple of terms here, and we want to take out a common factor. Now, the common factor is 9x plus 2 to some exponent. And let's take out the exponent, which is the smallest of these two. This exponent is understood to be 1 on 9x plus 2, and this is negative 1/2. Well, negative 1/2 we're going to snag out. All right, so it's 9x plus 2 to the negative 1/3. It's 1/3. And we're going to pull this as a common factor out of these two terms and see what happens. Now, when we pull this out of this term, we're pulling everything out, so we're left with 1. When we pull this out of this term, we're left with first 18, and then 9x plus 2 to some exponent, which will, when multiplied times this, which will cause us to have the 1 up here. So negative 1/3 plus what is 1? Negative 1/3 with 1 and 1/3 would give 1. 1 and 1/3, let's see, 1 and 1/3 is 4/3. Okay, so this is what we need. And now we can simplify a little bit farther. This negative exponent we probably wouldn't leave here. We would probably kick this down into the denominator and write this as our numerator. So we would have 1 plus 18 times 9x plus 2 to the 4/3 power. And then in the denominator, you see this rascal is just moving downstairs because of the negative exponent. And it is 9x plus 2 to the 1/3 power, or we could think of it as, gee, a fractional exponent implies a radical, and the index of the radical is the denominator of the fractional exponent. So this is the cube root then of 9x plus 2. Here's another one. Now, in this one, let's take out a common factor, and we know how to deal pretty much, I think, now with the binomial factor, but let's also achieve a form where we clear the fractions from the factored form. That is, from the, we're going to take out a common factor, and the other factor will not contain a fraction. Let me show you how to achieve that. Now, first of all, we want to be able to identify a common denominator. That is, we want to rewrite so that these fractions have a common denominator, and then we can take out a fraction containing that common denominator to clear the fractions from the other factor. Okay, here's how it goes. Between 5 and 4, the common denominator is 20. So let's see, we want 5 into 20 goes 4, 4 times 3, 12. This is 12/20ths. And I'll bring down the x plus 1 to the 5/3. And then once again, 4 into 20 goes 5. 5 times 3, 15. This is 15/20ths. And then x plus 1 to the 8/3. All right, now let's take out that common, a common factor. Well, between 12/20ths and 15/20ths, it's going to be some number of 20ths. The 12 and the 15, I think 3 is the common factor for those two. So we're going to take 3/20ths out of both of these terms. Now, we're also going to take out x plus 1 to some exponent. It's going to be the exponent which is the smaller of these two. Oh, that's 5/3. All right, so this is what we're snagging out as a common factor from these two terms. Now, let's see what's left. When we pull 3/20ths out of this, out of 12/20ths. That is, what do we need to multiply 3/20ths times in order to get 12/20ths? Oh, 4. You see, it's 4 over understood 1. 3/20ths times 4 over understood 1 is 12/20ths. All right, and that's the form we're trying to achieve here, where we have no fractions in this part of the problem. All right, now when we pull x plus 1 to the 5/3 out of this, oh, nothing's left. So we just have 4 as the remaining factor when we take this out of that. All right, then we slide over here. 3/20ths times what will give 15/20ths? So that would be 5. You see, 5 times 3/20ths would give 15/20ths. Okay. Now, we pull x plus 1 to the 5/3 out of this factor, and what's left? Well, it'll be x plus 1 to an exponent, which will cause these two to multiply and get that. You see, and now we're thinking exponents, so it's 5/3 plus what is 8/3? well, 5/3. Let's think of it as a mixed number. 5/3 is 1 and 2/3. 8/3 is 2 and, wow, maybe that's not the best way to do it. Let's think about it in thirds. 5/3 plus how many thirds to give 8/3? Oh, that would be 3/3. Okay, 3/3, oh, that's 1. So we would have this. I'm putting the 1 just for emphasis here. Normally we wouldn't write it. All right, so this then is our final form, without the 1 generally being written. Actually, though, we can clean up within the brackets. This is 3/20. I'm just bringing down here. And this is, I almost didn't see this. 5 times x plus 1 is 5x plus 5. So we would bring together the 4 and the 5 and simplify to 5x plus 9 over here. All right, there we go. In algebra, you talked about the domain in certain situations. Domain generally refers to the acceptable replacements for x in particular problems. That's one way to think about it. Now, in a problem like this, the acceptable replacements for x would be those values of x that will give us a value in this expression that makes sense to us. And it makes sense if we get a real number for the result of this. If we get a complex number, a number that's not real, then it doesn't make much sense. Now, for what values of x will we get a real number? Well, we can take the square root of positive numbers or 0. So the domain would be values of x that will cause the radicand to be non-negative. So we're looking for values of x that will cause x minus 3 to be greater than or equal to 0. And we can set up little inequalities like this a lot of times in order to help us with the process. So x then needs to be greater than or equal to 3. So our domain then would be x values greater than or equal to 3. Here it is. All right, if we have, no matter what that expression under the radical looks like, we might have been able to see it here, that gee, if x is 3, 3 minus 3 would be 0. So if x is any number greater than or equal to 3, you see, then we have valid values here when we take the square root. So we could kind of see through this situation and not have to set up the inequality. But there are certain situations like this where it's a little more difficult to see through. So it makes sense to say, gee, this makes sense as long as the expression 3x minus 2 is greater than or equal to 0. You see, and just solve this. So 3x is greater than or equal to 2. X then is greater than or equal to 2/3. So here then is our domain. Now when we have just a fraction involved, you know that in fractions the denominator of a fraction can't take on the value 0. Fractions involve division problems. We can't divide by 0. That's another way to look at it. So here, if we want the domain, the acceptable replacements for x, it would be any value, any real numbered value for x, except that one value of x that will cause the denominator to become 0. That value is 5. So we would say for the domain that x is not equal to 5. That's a way of saying it. Now, sometimes when a domain is listed, you list the exceptions for replacement like this. This is an exception. It would be all real numbers except that one. You see, so we're listing the exception. If we want to list all of the acceptable replacements for x, gee, in this situation, we would have to use maybe a notation like this. We can replace x with any real number in the interval from -infinity all the way up to 5, but not including 5, along with union the values in the interval from 5 to infinity. You see, so this then would be all of the acceptable replacements for x. The members of this set along with all the members of this set would be acceptable replacements. Now notice the parenthesis notation here to indicate 5 is not part of this interval, nor is it part of that interval. All right, now let's put the two ideas together. We have a fraction here. In the denominator of the fraction, we have a radical. So we have to think in terms of both the radical and in terms of the fraction. Now, just thinking in terms of the radical, We have acceptable replacements in the radical by thinking about values of this expression that will make it positive or 0. So we say that 3x minus 2 must be greater than or equal to 0. Now we did this situation just a moment ago. We found that in a couple of steps that x is greater than or equal to 2/3. Okay, fine. Now what about the notion of the overall fraction idea? Is this our domain for the overall expression? Well, not quite, because actually if x is equal to 2/3, the radicand becomes 0. The square root of 0 is 0, but 1 over 0 doesn't make any sense. So we have to take out the idea that x can actually be 2/3. So our domain here should be that x is greater than 2/3.